Hey guys, what's up? This is Mr. Myasis here, and in this video, I'm going to take a look at a few examples of what I call lookalikes, basically integration problems that look very, very similar but are different in technique. So we'll take a look at a few of these and just to kind of get you to take a look at, okay, these things look the same, but really what technique am I going to use? All right, so let's take a look at these four here that I have laid out. Dx over 1 plus x squared, dx over 1 plus x, x over 1 plus x squared, and 1 over 1 plus x all squared. So notice that they're kind of the same, but they have a little bit different in each of them. So let's take a look at the first one. And in the first one, all right, in the first one we have 1 plus x squared. Now there's nothing on the top, and plus x squared should tip you off that if there's nothing in the numerator but it's an x squared plus some other number in the denominator, we're probably going to use arctangent. And in fact, this one here is arctan of x, okay, where u is x and a was 1. Now, if we look at the next one here, there's no squared on that. So there's no squared in the denominator, means it can't be an arctan. And there's no number in the numerator. So if there's no number in the numerator, then this is simply a straight up logarithm one. So where the denominator is our inside of our log. So this is going to be ln of the absolute value of 1 plus x plus c. That's it. Now notice here in c, though, in c I do have an x squared in the denominator, but there's an x in the numerator. And if you looked at my last video with partial fractions, I always said there that we need to check to see if the derivative of the bottom, which in this case is 2x, could be on the top. In fact, it is if I just have a 2 here. So if I have a 2 here and a 1/2 here, I did a reverse chain rule. So this one is a reverse chain rule where my denominator is what I was taking the derivative of. So I'm going to have 1/2 ln of 1 plus x squared plus c. So see how that one's a little bit different there than the first one. Now in this case I don't really need the absolute values because 1 over 1 plus x squared is always going to be positive. Now we have the quantity squared in this case. Whenever we see a quantity squared or a quantity square rooted, then it's likely that we're going to end up bringing this up as a 1 plus x to the negative 2 power, and we're just going to use the power rule. So we're going to have 1 plus x to the negative 1 power divided by negative 1 plus c, and that's going to be our answer for that one. So notice here that these were all they were all similar looking, but very different in approach. Okay, let's take a look at these last two here. We've got integral of dx over x ln x, and the integral of ln x over x dx. So both of these cases, the ln x, the derivative of ln x is going to be 1 over x, right? So in both of these cases, I have the hook, right? I have the hook for both of them. The problem, the difference between the two is that in this case the ln is in the denominator, and in this case the ln is in the numerator. So if the ln is in the denominator, it actually becomes that whole thing there, and we have a reverse chain rule. If you want to think of it, okay, so let's just go ahead and we got the reverse chain rule. That's our hook. We're going to have, since it's in the denominator, we're going to have ln of what was in there, which was ln of x plus c. Now that's a quick way to do it. If you want to do it a long way, you can let u be equal to ln x, makes du equal to 1 over x dx, and we can just change this guy using a u substitution. So du is dx over x, so we already have a du there, and then u is ln x, so we have du over u, which is ln of u, plus c, which again gives us ln of x plus c. But if you can do the reverse chain rule, it's a lot quicker. Where in this case, ln is in the numerator, so that's really to the 1 power. So in this case, we're going to have ln x squared divided by 2 plus c. So that one we use a power rule. All right, so these are just some examples of things that look the same, but really are they look alikes. They look the same, but the process that we do them is different. All right, so there you go, guys. There's some mixed integration examples, and we're good to go. We'll talk to you later.